Hello and welcome to part 3 of my introduction to graph theory, and in this video I will cover Hamilton paths, Hamilton cycles, and isomorphisms. So first off we have a Hamilton path, which is a walk that covers every vertex exactly once. So say we have a graph that looks something like this, and we have a walk that starts here at v0, then it walks via this edge to v1, and then it walks over here to this final vertex v2. So v0, v1, v2 would constitute a Hamilton path. It is essentially just a path with the extra criteria of it requiring that it has walked over every single vertex, but every single vertex must have been walked on exactly just one time. And a Hamilton cycle is a walk, say walk that sorry, I moved the screen, is a walk that covers every vertex once except the starting point, which is supposed to be equivalent to the endpoint. So it is essentially just a regular cycle, except that it needs to cover every single, except that it needs to cover every single vertex in the graph. So although this is a Hamilton path, it is not a Hamilton cycle, since the starting point is not the same as the end point. So, however, if we had a walk that looked something like this, let's call this V0, it moves over here, we'll call this V1, we'll call this V2, and then it moves back via this edge to V0 again. So V0 is equal to V3, then V0, V1, V2, and V3 will be a Hamilton cycle. You could view Hamilton paths and Hamilton cycles analogously to Euler trails and Euler circuits, but just replace edge with vertex, and you essentially have the same concept. Now let's move on to isomorphisms. So iso means same, and morphism means different. And that seems like an oxymoron at first, but I'll show you why it makes sense. An isomorphism essentially just means that the algebraic structure of a graph is preserved. So suppose that we have two different graphs. One looks like this. Let's call this vertex A, this vertex B, this C, this vertex D, and both C and D connects to another vertex E down there. And we have another graph that looks something like this. Let's call this vertex capital A, this capital B, C, D, and then we have a capital E over here. Let's call this graph G1 and this graph G2. And the vertex set to G1, let's call it V1. It's just equal to A, B, C, D, E. And the vertex set to G2, let's call it V2, again equal to capital A, B, C, D, E. And they essentially have the same structure despite looking different, because you could view this edge AC analogously to this edge AC, this edge AB analogously to this edge AB, this edge BD analogously to this edge BD, this edge CD analogously to this edge CD, CE. Oh, I didn't write really straight. CE analogously to this edge CE, and this edge DE analogously to this edge DE. Well, this wasn't a very formal definition of what an isomorphism is, but hopefully this would have given you some intuition about what it is. So now, a more formal definition of an isomorphism would be that if two separate graphs, let's say G and G prime, with two separate vertex sets, let's say V and V prime, and two different edge sets, E and E prime. So if these two different graphs are to be isomorphic to each other, then there must exist a bijective function, let's call it f, that maps the vertices in G to the vertices in V prime, such that if Vi and Vi plus 1 is an edge in G, then the set containing f of Vi and f of Vi plus 1 must be an edge in the graph G prime. Now, let me show you an example where you could apply this definition to see that two different graphs have the same structure, despite it being quite hard to see. So suppose that we have a graph that looks something like this. Let's say this is vertex X, this is vertex Y, this is vertex W, this is vertex Z, this is vertex P, this is vertex Q, and there is a middle point vertex between X and Z that we'll call R, and there is also an edge between R and W. And we have another graph that looks like this. We'll call this A, call this B, we'll call this C, call this vertex F, we'll call this vertex E, and we'll call this vertex D. And also there is an edge connecting A to E, and there is a vertex in the middle that we'll call G that connects both to F and to D. Now we can since both of these graphs have the same amount of edges, we can create a bijective function between them. Let's say f of x is equal to d, f of y is equal to g, f of w is equal to f, f of z is equal to a, f of p is equal to b, and f of q is equal to c, and finally f of r is equal to e. Now let me zoom out a bit to make this a bit easier to see. So we could view this edge xq analogously to dc, since x maps to d and q maps to c. We could view xy analogously to dg, since x maps to d and y maps to g. We could view xr analogously to de, since x maps to d and r maps to e. We could view qp uh, analogously to uh, cb, since q maps to c and p maps to b. We could view pz analogously to ba, since p maps to b and z maps to a. Now we could view zw analogously to af, since z maps to a and w maps to f. And we could view wy analogously to fg, since w maps to f and y maps to g. We could view wr analogously to fe, since w maps to f and r maps to e. And finally, we could view the edge zr analogously to ea. So yeah, despite these two graphs not looking very similar, it's kind of hard to just eyeball it. They are isomorphic to each other, since they do have the exact same structure. That's what an isomorphism does. It preserves the structure. So let's take a very simple example where we could see whether or not two graphs are isomorphic or not. Suppose that we have one graph that looks like this with three vertices, and we have one graph that looks like this with four vertices. Now, it's very easy to see that these cannot be isomorphic to each other, since the vertices in an isomorphism is supposed to have a bijection to each other, which means a one-to-one correspondence, which is not possible if the two different graphs have a different amount of vertices. Now let's move on to a less trivial example. Suppose that we have a graph that looks like this. And one graph that looks like a pentagon. Oh, but let me redraw that. And now, are these two graphs isomorphic to each other? I'll give you some time to think about it. You can try to pause the video and answer in the comments. Now, it does look rather promising since uh, both graphs have three vertices with a valence of 2. These three vertices has a valence of 2, and these three vertices has a valence of 2. And it also has two different vertices with a valence of 3, and this graph has two vertices with a valence of 3. However, the key to figuring this out is by looking at this edge, and we'll see that the two different vertices with a valence of 3 are connected to each other in this graph. However, there is no edge connecting these two different vertices with a valence of 3 in this graph. So they cannot have the same structure, and hence they are not isomorphic, since there is a connection between these two vertices, while there is no connecting edge between these two vertices. And yeah, that's pretty much everything I had to cover for this video. So thank you for watching.